Today we have great pleasure to have an invited speaker from Oslo, Norway, Alberto. Alberto is, well, he's finishing up what he submitted his thesis. Soon to be Dr. Lopez holds an MSc in artificial intelligence and deep learning from the University of Alcalá, Madrid, Spain. He is currently pursuing his PhD at the end of it at the University of Oslo and the Institute for Cancer Research at the Oslo University Hospital under the supervision of Professor Tero Attokalio in the computational system medicine group. His research interests include data science, multimodal artificial intelligence, and bioinformatics, with a particular focus on developing practical and robust methods for real-world cancer research. Alberto and I met at the end of last year, and we found some great common ground in our research interests, especially working with incomplete data, which is a very real thing that's often put off or ignored in medical AI research. So he decided to come here to be a visiting researcher for the summer. So welcome, Alberto, and we look forward to your talk.
Okay, I should stay here. Okay. So when I started my PhD, I was so excited because I was going to work in PanCAN, a European consortium to improve pancreatic cancer using artificial intelligence and multimodal data. So it was a multi-center study collecting multiple types of information. So, you know, this was what I was expecting, like the perfect data. But then the reality was, how can I get this one? Okay. The reality was quite different. Like, welcome to the real world. And so yes, it was a multi-center study. And each center, the problem was that each center was collecting a different combination of modalities. So in the end, almost every patient had a unique combination of data modalities. So then the question was how to integrate all this information and still get a meaningful analysis. Thank you for being here. Let me share our project. Multimodal learning with incomplete data. I'm Alberto, a PhD student in the computational system medicine at the Institute for Cancer Research in Oslo, in Norway. So, of course, I want to thank my whole group for their support, and especially my supervisors, Tero Attokalio and John Sobolas. But going back to the topic, we realized from the very beginning that this was not, or we were not the only ones having this problem. So it was a very common problem across many fields, and not only research, also in industry and multimedia analysis, in autonomous driving. So it was a very general problem. I guess most of you are cancer researchers, so you may be familiar with the TCA data. It's a cancer database with a lot of omics modalities for multiple cancer types. So if we just consider 3 omics modalities, gene expression, methylation, and microRNA, we can really see that half or more than half of the patients have missing modalities. And this is just considering 3 omics layers. So imagine if we want to consider all of them, probably these numbers will go to 80 or 90%. And yeah, I know that you could say maybe that the TCA is a very old project. We have now improved a lot our protocols to collect better data, but I think this is not true. So this is a more recent paper, also in pancreatic cancer, published in Nature Cancer like 1.5 years ago. And they collected 74 pancreatic cancer patients with 6 modalities like genomics, transcriptomics, histopathology, proteomics, and so on. They had 74 patients, and then they built a predictive model, but they only used the patients with all modalities available. So that means that they went from 74 patients to only 39. So literally, they grew half of the data set. So imagine if you have been working in the wet lab, collecting all those samples, and then the bioinformatician in your team tell you like, well, if you wasted half of your work, because we cannot just include it in the analysis. So why they did this? The reason is that when you develop a predictive model, you always need that all your samples or your patients need have the same data. So if you develop, for example, a model for CT scan and genomics, all your patients need to have both modalities. Some patients don't have both modalities. You just cannot apply your model. And I guess, I'm not sure if some of you work in clinical trials. In clinical trials, it's true that we try to control all the conditions. So maybe this is not a very relevant problem in clinical trials. Only 5% of data is actually missing. But also we have to remember that clinical trials represent just 3% of the patients. So when we go to the real world data, that means all the patients that go to the hospital, 80% of the data is missing because, well, we don't apply the same test to all patients. And also, many of these modalities are only collected in research projects. So then my question is, why are we all building all these predictive models with perfect accuracy if then we cannot apply it in the real world because we don't have the data? So I think we should work more on building more applicable and useful predictive models that we can use in the real world situations. So when we face this problem, we typically have three options. The first one is just to use only those patients with all modalities available, but that means that we are going to lose a lot of information. That in this case, where they could only use half of the data set. The other option is to reduce the number of modalities that we want to analyze, or even just using one of them. Again, maybe we are not able to analyze all the samples. And also, I think we all agree that cancer should be addressed from a multi-perspective analysis. So if we don't use a multi-modal data set, we are losing the global perspective that a multi-modal data set can give us. And then the last option is just, for example, if you have gene expression and you have some missing values, you can just apply a simple imputation technique where you try to estimate the missing values. But many times this is just introducing noise, so the model can become even worse. So we need more methods or better methods to deal with this problem. And actually, the number of papers mentioning this problem or trying to address this problem is exponentially growing in the very last few years. So it's a very common problem nowadays, or it's actually growing. So this is why we built iMML, a framework for Python package for multi-modal learning with incomplete data, where we try to integrate all the methods that were already available, so you can have everything in just one framework. So your life can become more easy, or your analysis. So let's say that you have multiple sources of information, like pathology reports, CT scan, omics data. As I said before, if you want to build a predictive models, typically all your patients, all your samples need to have all the modalities. So this is the key here, not all the samples need to have all the modalities. For example, the sample number 2 doesn't have the modality number 2. And when I say sample, it's just your representation. So it can be a patient if you're working with a patient cohort, it can be cell. If you're working in single cell data, users, if you have a web application. So it's just your observations. And then also the missing data can be at 2 levels. So it can be a modality level, which means the patient or the sample doesn't have the modality at all. Like it doesn't have gene expression, for example. And it can be also at the feature or variable level, which means the patient has gene expression, but maybe some genes couldn't be reached. So this is the input for our package, and then you can use iMML for multiple machine learning tasks, classification, patient stratification, biomarker discovery, to explore your data, create visualization. So the key features, first, we integrated more than 25 methods for analyzing complete multi-modal datasets. We made a strong effort to have a good documentation so you can apply the methods effectively. Also, we try to have a very simple interface. So even if you are not familiar with programming, you actually just need 2 lines of codes. And if I can yes, so you just need 2 lines of code, one to define your algorithm, in this case, a string algorithm, and a second line to fit your model in the predictions. So it's very easy to use. And it's also open source, so it means everybody can use it, and even if you develop a new method, you can integrate it so that more people can use. Let's see first an example of a pipeline, a multimodal clinical application. So if you have, for example, clinical data, histology image, and some text reports, your dataset could be complete or incomplete. You can load it using your favorite Python framework like Pandas, NumPy, PyTorch is compatible with widely used Python tools. You can create some visualizations. For example, in that case, we show how many samples or how many patients you have depending on the combination of data that you want to use. We have also a model for multi-modal statistics where we try to estimate how redundant is the information between 2 modalities. For example, if you see that the redundancy between 2 modalities is very high, you can just simplify your problem and just use one thing. And then, of course, you can train your model, predict on new samples, and even if they have missing modalities, or you can also evaluate your model using our framework, because we have common strategies like cross-validation, train test splitting, and simple strategies. So we have already applied this in several use cases from multiple domains. You are cancer researchers, and actually our initial goal was to apply this on pancreatic cancer patients for patient stratification. I would like to show this application where we try to, as I said, stratify patients, pancreatic cancer patients in high risk and low risk. So why pancreatic cancer? First, well, because it's probably the most aggressive cancer disease. I think only 10-12% patients survive more than 5 years. And actually, about 80% die in the first 2 years. And this is because it's very difficult to identify the symptoms. Also, we don't have good biomarkers, and the treatment response is usually very poor. So this project was was actually carried out by Alejandra and Rafa, two of our members in our group. So for this project, we took the TCGA dataset with 6 omics modalities: gene expression, microRNA, methylation, copy number alteration, mutations, and proteomics. We first wanted to evaluate what specific modality combination was the best. So we tried all possible modality combinations. We also wanted to identify the optimal number of groups and the best clustering algorithm for this dataset. So we tried 9 clustering algorithms, all of them were available already in our framework. To make a fair comparison for this first experiment, we use only those samples with all modalities available, because this is an incomplete multimodal dataset. In general, I think we have 172 patients, but only 89 patients had all modalities available. So to make a fair comparison for this first experiment, we only use those patients with all modalities available. So first, we saw that methylation and copy number alteration was the best combination of data modalities. We also found that 2 was the optimal number of clusters. And then for how to evaluate the algorithm, we have to remember that in the end, even though in this first experiment, we are only using those patients with all modalities available, but in the end, the goal is to analyze all the patients, even if they have incomplete data. So what we evaluated is how robust was the algorithm when you have more and more missing data, and incomplete samples. So we saw that MIMO was actually the most robust algorithm. So now we have the best combination of data, the optimal number of clusters, 2, and the best or the most robust algorithm. So now we apply this setting to the whole cohort, where now we have incomplete data. So we found 2 clusters, one with 33 patients, another cluster with 120 patients. This figure shows that the clusters are very stable. Also, you can see that the pattern is very clear, that the cluster number 2 have a much higher copy number burden, also have higher methylation values, and the difference is significant. Then we also wanted to see if the clusters have a significant association to some clinical variables. For example, we found that it was significantly associated to the tumor mutational burden, which is an important biomarker for immunotherapy. Again, with the cluster number 2 having higher values. Also, the clusters were clinically very relevant because they had a significant survival difference in terms of overall survival and also disease-free progression, especially in the first 2 years, because as we said, most of the patients die in the first 2 years. So after this point, we only have like 2-3 patients, so it's almost impossible to find significance after these 2 years. We also compare our groups with previously reported molecular subtypes, and we found that it was different. So it means that the clusters were novel. And we also wanted to evaluate if our clusters were more relevant in terms of prognosis. So we found that for many evaluations, our clusters were one of the best. So I wouldn't say our clustering approach is like the best always, but I think we have or we provide a very good alternative. For example, has the highest signal to noise ratio, which I think is very good. And then, so now that we are sure that the clusters were relevant, so to build this clustering, you need the whole omic modality, right? But this is not common in the clinical practice, and because it's quite expensive, I would say. So we try to identify just a minimal biomarker panel, a few biomarkers that allow us to stratify the patients. So we applied a multi-modal feature selection where we found that using only 3 CpG sites, 3 methylation values, is already enough to stratify the patients. But also, as our initial goal was to make a useful model for real-world situations, I think methylation data is not or has some issues in the real world. First, it's not the most common omic modality available. And second, the values depends on the platform that you are using. You also need to apply some batch effect correction. So it's not very easy to use. So then we decided to focus more on the copy number alteration, because first, I would say genomics is the most common omics data. And second, the values are very independent. So it's not depending on the platform that you are using, or you don't need to apply a batch effect correction. Like if you have 2 copies, you have 2 copies. There is no relative value set. So we applied the feature selection just on the copy number, and we found that only for deletion or the deletion for login was good enough to stratify the patients. Yes, so these were actually the 4 deletion, the 4 login that we need to stratify the patients. We also try to explain molecularly the stratification of the patients. So we saw that the cluster number 2, the one that had a lower or worse prognosis, was enriched in a KRAS dependency signature, and this KRAS has been, or it's very well known to be associated to pancreatic cancer. Also, when we analyzed the proteomics data, we saw that this cluster number 2, or the patients here, had mTOR pathway downregulated, which is a very common also pathway that's involved in many biological processes. So the final step that we applied was, okay, now we have a model. So we have shared and openly the model. So if you want to test it in your cohort, you can use it. And you only need these 4 biomarkers. We actually already validated the model in a completely independent cohort. In this case, pancreatic cancer patients from the PDAC consortium. And here we were able to reproduce almost, or I would say, all the conclusions that we found in the TCGA dataset. So again, the clusters were significantly different in terms of survival. Also, they were significantly associated to tumor mutational pattern. The biomarkers were related to the overall survival. So it has some meaningful points. The biomarkers have relevance also in this data. So in general, this was an example on how we applied iMML in pancreatic cancer subtyping, where we first tried to find the best combination of data modalities. That was copy number alteration and methylation data. We found 2 clusters where the cluster number 2 was characterized by higher mutational burden, also had lower survival probability and higher tumor recurrence. And we shared a model that only needs biomarkers, and we validated this model in an independent cohort. So in general, I would say that multimodal data sets are more and more available, but they usually are incomplete. So we try to build this framework so that it's easier to analyze them. And finally, I came here to Montreal, to Enger Lab, to work with Eugene Enger, the group leader, and also Eugene, the PhD student. They had a data set with clinical variables and pathology reports and consultation notes. And they already found that using the LLM to extract clinical variables was very useful for outcome prediction. And now we want to see if we can actually use the large language models, the LLMs, to uncover some hidden information that we that could be in the text, and also to try to integrate it with histology images. And as this is actually an incomplete multimodal data set, so not all patients have all modalities. So that's why we want to analyze. And I will be here for 3 months, more or less. If you are interested in using it, you can directly use the documentation. But if you want actual collaboration, I would be very happy if you can contact me. Another question is, how can I help you in your projects? Thank you.
All right. So much. Thank you so much, Alberto. Anyone has a question here or at the Glen?
I'll ask the question.
Go ahead.
How little, what's the most missing information you can have that everything is false to? 80% is like.
I'll repeat the question first. Yeah. Pete's question is, yeah, how little information.
Before you can still make something.
Yeah, how little information can you reliably integrate into a multimodal framework before it's too little? Everything falls apart.
Yeah, so I think that really depends on the problem, because also it depends on how relevant is that modality. At least in our experiment, it was here. So at least in our experiment, we found that even when only 20%, when only a modality is available for 20% of the patients, you can have almost or very similar performance that using the whole data set. So that was our experience. At least I don't know if I can make a general conclusion.
Sure, I realize it's a little bit.
Yeah.
This was for the pancreatic.
Yeah, for pancreatic cancer and using omics data.
I guess if the data you have is really good, it makes up for the missing.
The what?
So if the data that you do have is like it has quality information, you can get away with missing more versus if you have data, but you have a lot of data, but it's not particularly useful at pulling something out. And
yeah, so something that we are trying to use with her actually in her project, I think we have. Yes, so here, so some of the methods that we do is to try to estimate the redundant information that or how much information can you have on each modality for a particular task. So in the dataset that I showed, that I'm going to work here, I would say only 10% of the patients have histology images. So some possible solutions to try to measure how useful is that information. Because if it is not useful at all, you can just discard that modality.
So that's the partial information decomposition, so you can get a sense of how much mutual information there are for different modalities. But you have to do that for complete data, I guess.
Well,
as a test, as a pre-processing.
Yes, you can try to estimate the missing values that you have, but yes, you need all fully observed data.
I saw that's what you guys did for the pancreatic cancer as well. The first step to find out which what's the best method to carry forward for the entire data set. That was carried on the half of the data set that has a complete sample.
Yes, so because here we were considering 6 omics modalities, but maybe not all of them are useful for our task, or they are redundant, or they are not relevant for the task. So the first step that we applied here was to try to identify what's the best combination of data modalities so that it was possible.
Sure.
So in your software, are you just investigating which combinations of modalities to use, or are you actually creating synthetic data as well?
So
I'll just repeat the question. Shreen's question was, so in the iMML software, are you also creating synthetic data as well as an imputation approach as opposed to others imputation approaches?
So we have integrated multi-modal methods in our framework. So this really depends on how the method address that challenge. So some methods try to estimate the missing values, and other methods just are like free imputation methods. So they directly can analyze the data without imputation. That answer? Yeah.
So I have a question about, I guess, biomarker discovery, the process. So it seems like the pipeline of your pancreatic workflow is that you first go ahead with a complete data set and just to see what is the best approach to, what's the best clustering technique and whatnot to be applied to the entire data set. And then, because clustering is an unsupervised approach, so do you define how many clusters you want to see, or that's just something that's naturally found in your algorithms? And then after you found those clusters, you do some retrospective analysis of the specific transcriptomics and other gene features to go backwards to discover which biomarker actually matters. Is that how it works?
Yes, so the number of clusters is typically a hyperparameter. So you usually try to optimize it, or some methods can actually try to estimate. So, but usually it's something that you have to define. So again, we just make a benchmarking. So we evaluated that happen when we have 2 groups, 3, 4, 5. What's the best option? And then for the second, yes, so unsupervised clustering typically can help you discover like new knowledge. It's not like supervised, because in supervised it's more like trying to automate something. In unsupervised, you try to discover something that you don't know. So once we were able to stratify the patients, now we wanted to analyze why this has happened. So that's why we went backward to try to find the biomarkers that are defining the clusters.
And you had a figure of going down to 3 biomarkers. Could you go back to that? It's the one last one.
I think it was this one.
Yeah, and could you just explain that a little bit further on how did you reduce that to find out the 3 biomarkers from the very, very high dimensional features?
Yeah, so this was just a feature selection algorithm.
Okay.
There are tons of them.
Like feature reduction?
Yeah.
thing?
So it's just a feature reduction in that sense.
I just have a more general curiosity question, but was the creation of this package something that you set out to do for your PhD, or was it something that was born out of a tool that you actually needed to do your project?
Yes, so
I'll just repeat it for the audience. Jonathan's question is whether this package is something that was initially set out to do at the beginning of the PhD, or a tool that you created to solve other problems during the PhD?
Yes, so the initial problem was, if I can reach
that huge consortium was the original goal.
Yes, that was the initial goal, like how to integrate all this information. So the initial idea was just to apply probably like the best method and focusing on the results, let's say. But this was made like a couple of years ago, so the landscape of methods were like very heterogeneous. Not many methods were available. They were, you know, how developers create methods, so they were very diverse. They had software conflicts and things like that. So the creation of the package was more initially like a side project to try to have a simple interface to apply all the methods. But then we also realized that this was a very common problem. So that's why we also try to make it more important.
So in terms of other applications rather than patient stratification, which is what I'm familiar with, you mentioned that there are some other applications in the cancer domain, such as cell lines and whatnot.
Yes, we have applied. We have actually created a large-scale benchmarking where we compare, I think it was 20 datasets and 30 algorithms to try to actually create this hierarchy of what methods are better. We have applied our framework in drug discovery also. I think, yeah, so pretty much those were the applications that we already have. We are working also in single cell data, but it's not finished.
Cool, thank you. So, simple questions, I guess. Nothing on the from the Glenn side. So thank you so much, everyone. We're finishing a bit early today, but have a great lunch. Thank you, Alberto, again. Bye.